March 1943, the mid-Atlantic, 400 miles from any coastline. A British Royal Navy escort ship called a Sunderland flying boat overhead, and inside that aircraft's belly, a screen the size of a dinner plate glows green in the darkness. A blip appears. A small one. Too small for a ship, too small for a whale, too small for anything except the one object every Allied airman has been hunting for 3 years and has almost never found at night. The conning tower of a surfaced U-boat, recharging its batteries 15 miles away, invisible to the naked eye, invisible to searchlights, invisible to every radar Britain has ever built before this one. The pilot banks toward the blip.
40 minutes later, oil and wreckage mark the spot where U-boat number 77 used to be. The submarine never saw the aircraft coming. It never heard it. It never had a chance. Because for the first time in the history of warfare, a machine had learned to see in absolute darkness better than human eyes could see in daylight.
That machine was the size of a loaf of bread, made mostly of a solid block of copper. And it had been invented 11 months earlier by 2 physicists in a basement laboratory in Birmingham who had no idea they were about to win the Battle of the Atlantic.
Britain in 1939 had one fundamental vulnerability that no amount of courage or strategy could fix. It was an island nation that imported nearly everything: food, oil, raw materials, weapons components shipped from America. 60% of Britain's food came by sea. Almost all of its oil came by sea. If German submarines could cut the sea lanes faster than British shipyards could replace the losses, Britain would starve and stall before a single German soldier ever crossed the Channel. Winston Churchill understood this with total clarity. He later wrote that the only thing that ever really frightened him during the war was the U-boat peril. Not the Blitz, not the threat of invasion. The U-boats. And the U-boats were winning. Germany's submarine commander, Admiral Karl Dönitz, had built his entire strategy around a brutally simple insight. A submerged U-boat in 1939 was nearly blind and nearly deaf, crawling along at 6 or 7 knots on electric batteries that lasted barely a day. But on the surface, running on diesel engines at 17 knots, a U-boat was a fast, nearly invisible hunter, especially at night. Surfaced submarines were low, dark, and small. Lookouts on convoy escorts, straining their eyes across heaving black water in a North Atlantic gale, routinely failed to spot a U-boat conning tower until it was already inside the convoy, torpedoes in the water. Dönitz's wolf packs exploited this blind spot with savage efficiency. They attacked on the surface, at night, threading between escort ships that simply could not see them coming. In May alone, they sank 115 ships in the Western Atlantic, and the toll for June was 122. German U-boat crews called these stretches the happy time, not once, but twice. First in 1940 and again in early 1942 off the American coast, where merchant ships sailed silhouetted against the undimmed lights of seaside cities, perfect targets for submarines that needed only to wait in darkness and fire. Britain already had radar, and it was already one of the most closely guarded secrets of the war. Robert Watson Watt's chain of coastal stations had tracked incoming German bombers since before the war began, feeding data into the fighter control system that won the Battle of Britain. But that radar operated on long radio wavelengths, a meter or more, which meant the antennas had to be enormous. Arrays of steel towers bolted to hillsides, utterly impossible to fit inside an aircraft. And even if you could shrink the antenna, long wavelength radar had a second, crueler problem. Its beam was so wide and unfocused that it could distinguish a coastline from open ocean, but it could never pick out something as small and low as a surfaced submarine hull lost in wave clutter. The physics were unforgiving. To detect something the size of a U-boat conning tower, you needed radio waves with a wavelength close to the size of the object itself, somewhere around 10 centimeters, what physicists called microwave or centimetric radar. And in 1939, nobody on Earth could generate microwave radiation with enough power to be useful. The vacuum tubes of the era, klystrons and the like, produced microwaves, but only a few watts of them, a flashlight trying to illuminate a stadium. The man who would solve this problem had spent the first part of his career failing at something else entirely. John Randall was a physicist working on luminescent materials, the glowing paint used on instrument dials and gun sights, when the Air Ministry pulled him into radar research in 1939. He was paired with Harry Boot, a younger physicist fresh out of Birmingham University, with almost no experience in vacuum tube design. Precisely the kind of pairing that sometimes produces breakthroughs because neither man is burdened by knowing all the reasons something shouldn't work. Their boss at Birmingham, Mark Oliphant, gave them a brutally direct assignment in late 1939. Find a way to generate high-power microwaves, because Britain's existing long-wave radar would not survive contact with German countermeasures and could never solve the submarine problem regardless. Randall and Boot inherited an existing device called the magnetron, invented decades earlier and refined by various researchers since, which used a magnetic field to spin electrons in a circular path inside a vacuum tube to generate radio waves. The conventional magnetron worked, but weakly. Randall and Boot's insight, developed through trial, error, and a design sketched in chalk and built with whatever metal they could scrounge from the university workshop in wartime Britain, was to replace the magnetron's simple internal structure with a solid block of copper, machined with multiple resonant cavities arranged around a central circle, like chambers in a tiny mechanical heart. Their first working example, built and tested on 21 February 1940, produced hundreds of watts at 10-centimeter wavelength, an unprecedented achievement. Hundreds of watts does not sound like much. It was, in the context of microwave generation, like going from a candle to a searchlight in a single afternoon. Within weeks, engineers at the General Electric Company in Britain had improved the design further. Within months, they had pushed it to well over a kilowatt, then 25 kilowatts, then over 100 kilowatts by 1941, climbing toward a megawatt by 1943. The cavity magnetron, this strange, dense lump of machined copper, had gone from laboratory curiosity to the most powerful microwave source on the planet in less than a year. And it had done so inside a country that was, at that exact moment, being bombed nightly and bracing for invasion. What made the cavity magnetron so transformative wasn't simply that it produced more power. It was that the power came packed into a device small enough to carry. The high-power pulses were generated from a device the size of a small book and transmitted from an antenna only centimeters long, reducing the size of practical radar systems by orders of magnitude so that they could be installed in fighter aircraft. Everything that had made centimetric radar physically impossible in 1939, the giant antennas, the weak signal, the inability to resolve small targets, evaporated within 18 months. Suddenly, a radar set could ride inside the nose of a bomber, the wing of a coastal patrol aircraft, or the bridge of a small escort corvette barely larger than a fishing trawler. New radars appeared for night fighters, anti-submarine aircraft, and even the smallest escort ships. And from that point on, the Allies of World War II held a lead in radar that their counterparts in Germany and Japan were never able to close. Britain's leadership understood almost immediately that they were holding something extraordinarily dangerous to share and extraordinarily dangerous to lose. In the late summer of 1940, with German bombs already falling on London and the threat of invasion entirely real, Churchill made one of the strangest gambles of the war. He sent a delegation to the United States carrying, among other secrets, an actual cavity magnetron to ask the still neutral Americans for help building it into a deployable weapon faster than Britain's own struggling wartime industry could manage alone. The Tizard mission, named for the scientist who led it, handed over a technology so far ahead of anything American researchers had seen that the visiting British scientists were initially suspected of exaggerating. The magnetron was revealed to the United States in 1940 during the Tizard mission, and local development began at the MIT Radiation Laboratory within a matter of weeks. What became known as the Rad Lab would grow into one of the largest scientific efforts of the war, eventually employing thousands of researchers and producing roughly half of all the radar equipment used by the Allies, an entire arm of American wartime science built around a chunk of British copper carried across the Atlantic in a black box, almost too valuable to risk on the crossing. The device that emerged from this frantic transatlantic collaboration and went to sea aboard Allied aircraft was called ASV Mark III, Air-to-Surface Vessel Radar, the direct descendant of the chalk sketches Randall and Boot had drawn on a Birmingham blackboard. For the U-boats, it was catastrophic, and at first they had no idea why. German submariners had grown confident in a piece of equipment called METOX, a passive receiver that could detect the radio emissions of older, long-wavelength Allied radar and warn a U-boat captain to dive before an aircraft got close enough to attack. METOX worked reasonably well against the old radar. It was completely deaf to centimetric wavelengths. None of the existing German receivers could operate at the magnetron's 10-centimeter wavelength, and the introduction of ASV Mark III in particular led to significant losses among the U-boat fleet during the summer of 1943. German U-boats that had spent years surfacing confidently at night to recharge batteries and run at high speed now found Allied aircraft appearing out of total darkness with no warning at all, attacking from directions the crew never saw coming, dropping depth charges with an accuracy that seemed almost supernatural. Crews began whispering rumors that the British had developed some kind of infrared detector that could see the heat of a diesel engine, or even that they had a sixth sense, because the alternative explanation, that the British could somehow see them through total darkness at a range of many miles, seemed too far beyond what physics in 1943 should allow. The numbers tell the story with brutal clarity. The first half of 1942 had been one of the worst stretches of the entire war for the Allies. Allied shipping losses rose from 50 ships per month in January 1942 to a peak of 124 per month in June 1942. Britain's supply lines were hemorrhaging faster than American shipyards, however furiously they worked, could possibly replace the losses. Churchill's own diaries from this period describe nights of genuine dread, calculations of how many weeks of fuel and food reserves remained if the trend continued. Then, across 1943, the entire shape of the battle inverted. Allied shipping losses gradually dropped to just 4 ships per month by June 1943, while German U-boat losses, which had remained below 15 per month for most of the war, peaked at 37 in May 1943 alone. Centimetric radar was not the only reason for this reversal.
Code breakers at Bletchley Park had cracked the German naval Enigma cipher, giving Allied convoy planners advanced knowledge of U-boat positions. Long-range aircraft finally closed the mid-Atlantic air gap, where U-boats had previously operated free of any air patrol whatsoever. Escort carriers and dedicated hunter-killer groups gave the Allies, for the first time, enough ships to hunt submarines rather than merely defend convoys. But these other advantages worked because radar made them work. Knowing roughly where a U-boat pack was hiding from decoded radio traffic meant little if patrol aircraft still could not actually find a surfaced submarine in the dark once they arrived in the area. Centimetric radar was the sense organ that turned intelligence into kills, turned a hunter-killer group's general suspicion into a precise depth charge pattern, landing exactly where a submarine sat on the surface, unaware it had already been found.
The British historians who studied this turning point afterward settled on May 1943 as the unambiguous hinge of the entire Battle of the Atlantic. The month German losses overtook Allied losses for what would prove to be the rest of the war. In May 1943, outstanding defense of convoys compelled Dönitz to change his U-boat strategy in the North Atlantic, although he still had more than 200 submarines remaining, and German industry was rapidly replacing losses. Dönitz himself, in a private moment captured afterward in post-war accounts, admitted to colleagues what amounted to a confession of total defeat in the theater he had spent the war believing could win it outright for Germany. He pulled his wolf packs out of the North Atlantic that month, not because Germany had run out of submarines, but because submarines that could no longer hide in darkness were no longer weapons. They were targets. The technology did not stay secret forever, and its capture illustrates exactly how seriously both sides understood what was at stake. A related British system, codenamed H2S, used the same cavity magnetron technology to let bombers map the ground beneath them through cloud cover, and it was so prized that crews flying with it were ordered never to risk capture, with some aircraft fitted with explosive charges meant to destroy the magnetron rather than let it fall into German hands intact. The development of the cavity magnetron was so sensitive that aircraft were not permitted to fly over Germany with it until 1943, and they were fitted with explosives to destroy the magnetron if the plane was shot down, to ensure the enemy could not learn about the device. The precaution failed exactly once, and once was enough to terrify British intelligence for the rest of the war. On its second operational mission, on the night of 2 to 3 February 1943, an aircraft carrying an H2S set was shot down, and the device was captured almost intact by German forces, and a second unit was recovered a week later. German engineers, led by a young physicist named Otto Hachenberg, dismantled the captured magnetron and produced a detailed technical report identifying exactly what they had found and exactly how dangerous it was. Combined with intelligence gathered from the surviving aircrew, German researchers correctly identified it as a ground mapping system and worked out its method of operation, though the British radar team had separately calculated that it would take Germany roughly 2 years to develop an equivalent centimetric radar of their own, even with a captured example in hand. That calculation proved exactly right, and it proved decisive. A naval detector capable of picking up the new centimetric radar did not reach German U-boats until late 1943, and even then provided a detection range of only about 8 kilometers, far too short to give a submarine meaningful warning before an aircraft was already overhead. By the time Germany understood what had been hunting its submarines in the dark, the technological race was already over, and the Atlantic was already lost. What makes this story compelling as more than a tale of clever engineering is the asymmetry at its heart. Britain did not win the Battle of the Atlantic by building more submarines, more destroyers, or more bombs. It won by solving a sensory problem. The U-boat had not become a weaker weapon between 1939 and 1943. The same hull, the same torpedoes, The same trained crews that had terrorized convoys in 1940 and 1941 were still out there in 1943. But they had lost the one advantage that made them deadly: the cover of darkness. Stripping that advantage away required physicists working at the very edge of what vacuum tube engineering could achieve, an international transfer of secrets so sensitive it was carried across an ocean in wartime in a single physical box, and an industrial mobilization on 2 continents to turn a laboratory curiosity into tens of thousands of deployable units fitted into aircraft, ships, and bombers within roughly 3 years of the original chalk sketch. Randall and Boot, the 2 physicists who built the first working cavity magnetron from scrap metal and a borrowed vacuum pump in a Birmingham basement, received comparatively modest recognition for it at the time. For their work on the magnetron, Randall and Boot were awarded the Thomas Gray Memorial Prize of the Royal Society of Arts in 1943 for improving the safety of life at sea. A strikingly understated description of a device that had just turned the tide of the largest and longest naval campaign of the Second World War.
There is a particular kind of historical irony in how this story ends. The cavity magnetron, the device that let Britain finally see U-boats hiding in total darkness, did not stay a wartime secret confined to military archives. Within a decade of the war's end, the same resonant cavity principle that generated lethal pulses of microwave radiation for submarine hunting had been repurposed for an entirely domestic application: heating food. The household microwave oven, patented shortly after the war by an engineer who had worked on magnetron production and noticed a chocolate bar melting in his pocket near an active radar set, descends directly from the same copper block that once hunted U-boats across the North Atlantic. A technology built in desperate secrecy to find an enemy invisible in the dark ended up, within a single generation, sitting on kitchen counters across the world, used by people who had never heard the names Randall, Boot, or Donuts, reheating leftovers with the great-grandchild of a weapon that once decided whether an island nation would starve. The deeper lesson of the Battle of the Atlantic's turning point is not really about radar at all. It is about the nature of decisive advantage in war. Germany entered the submarine campaign with a genuinely superior tactical doctrine: attack on the surface, at night, exploiting a sensory blind spot that no convoy escort could overcome through courage or training alone. That doctrine worked brilliantly for nearly 4 years, precisely because it exploited a hard physical limit: the simple fact that human eyes cannot see in darkness. And 1939-era radar could not resolve a target as small as a submarine hull. Britain did not defeat that doctrine by outfighting it. Britain defeated it by making the underlying physical limit disappear. Once a U-boat on the surface at night was exactly as visible to an Allied aircraft as a battleship at noon, the entire German strategic concept collapsed at once. Not gradually, but within a matter of months, because it had never been a strategy independent of the darkness it depended on. Take away the darkness, and you do not have a weakened U-boat fleet. You have a fleet of slow, fragile, lightly armed steel tubes with nowhere left to hide. None of this came without cost, and the final tally of the Battle of the Atlantic makes clear how close the margin actually was before microwave radar tipped it. By the war's end, the Allies had lost roughly 3,500 merchant ships and 175 warships in the Atlantic, alongside tens of thousands of merchant seamen and sailors who never got the chance to know whether the technology racing toward the front lines would arrive in time to save them. The Germans paid an even steeper price for a campaign that ultimately failed. 783 U-boats lost, nearly 3 out of every 5 German submariners killed by war's end, a casualty rate almost unmatched by any other branch of any other military in the war.
Donitz had built a service around young, aggressive officers competing for tonnage sunk, and by 1944, that same service had become, almost overnight, one of the most lethal places a German serviceman could be posted. Not because the boats had gotten worse, but because the ocean itself had stopped offering anywhere to hide. Strategically, the implications reached far beyond shipping statistics. Had the U-boats won the tonnage war in 1942 or early 1943, before centimetric radar reached the fleet in numbers, there would have been no buildup of American troops and equipment in Britain sufficient to launch a cross-channel invasion in 1944. The Normandy landings depended on a year of uninterrupted convoys delivering men, tanks, fuel, and ammunition across an ocean that German doctrine had been built specifically to deny. In that sense, the chalk sketch on a Birmingham blackboard in late 1939 belongs on the same short list of inventions that shaped the war's outcome as the atomic bomb or the breaking of Enigma, not because it was more destructive, but because it removed almost surgically the one advantage an entire branch of the German military had staked its existence on.
That is what Randall and Boot built in a Birmingham basement with chalk, scrap copper, and a problem they had been told more or less was unsolvable. Not a bigger gun, not a faster ship, a way of seeing that the enemy had never imagined anyone could possess, until the night it appeared on a radar screen as a small green blip in the middle of an empty, lightless ocean, and the war in the Atlantic was already over before anyone on the submarine below even knew it had begun.